How to peek inside binary files from the Linux command line. Have a mystery file. The Linux file command will quickly tell you what type of file it is. If it's a binary file, though, you can find out even more about it. File has a whole raft of stablemates that will help you analyze it. We'll show you how to use some of these tools. Identifying file types. Files usually have characteristics that allow software packages to identify which type of file it is, as well as what the data within it represents. It wouldn't make sense to try to open a PNG file in an MP3 music player. So it's both useful and pragmatic that a file carries with it some form of ID. This might be a few signature bytes at the very beginning of the file. This allows a file to be explicit about its format and content. Sometimes, the file type is inferred from a distinctive aspect of the internal organization of the data itself, known as the file architecture. Some operating systems, like Windows, are completely guided by a file's extension. You can call it gullible or trusting, but Windows assumes any file with the docx extension really is a docx word processing file. Linux isn't like that. As you'll soon see, it wants proof and looks inside the file to find it. The tools described here were already installed on the Manjaro 20, Fedora 21, and Ubuntu 20.04 distributions we used to research this article. Let's start our investigation by using the file command. Using the file command, we've got a collection of different file types in our current directory. They're a mixture of document, source code, executable, and text files. The ls command will show us what's in the directory, and the hl, human readable sizes. Long listing option will show us the size of each file. lshl. Let's try file on a few of these and see what we get. File build _instructions.ot. File build _instructions.pdf. File cobol report April 60, DJVU. The three file formats are correctly identified. Where possible, file gives us a bit more information. The PDF file is reported to be in the version 1.5 format. Even if we rename the ODT file to have an extension with the arbitrary value of XYZ, the file is still correctly identified, both within the file's file browser and on the command line using file. Within the file's file browser, it's given the correct icon. On the command line, file ignores the extension and looks inside the file to determine its type. File build _instructions.xi. Using file on media, such as image and music files, usually yields information regarding their format, encoding, resolution, and so on. File screenshot.png. File screenshot.jpg. File pocklebell _canon _in _d.mp3. Interestingly, even with plain text files, file doesn't judge the file by its extension. For example, if you have a file with the C extension, containing standard plain text but not source code, file doesn't mistake it for a genuine C source code file. File function plus headers, H. File makefile. File hello, C. File correctly identifies the header file, H, as part of a C source code collection of files. And it knows the makefile is a script. Using file with binary files. Binary files are more of a black box than others. Image files can be viewed. Sound files can be played. And document files can be opened by the appropriate software package. Binary files, though, are more of a challenge. For example, the files, hello, and wd, are binary executables. They are programs. The file called wdo is an object file. When source code is compiled by a compiler, one or more object files are created. These contain the machine code the computer will eventually execute when the finished program runs, together with information for the linker. The linker checks each object file for function calls to libraries. It links them to any libraries the program uses. The result of this process is an executable file. The file, watch.x, is a binary executable that has been cross-compiled to run on Windows. File wd. File wdo. File hello. File watch.x. Taking the last one first. File tells us the watch.x file is a PE32 plus executable console program. For the x86 family of processors on Microsoft Windows, PE stands for Portable Executable Format, which has 32 and 64-bit versions. The PE32 is the 32-bit version, and the PE32 Plus is the 64-bit version. The other three files are all identified as executable and linkable format, ELF, files. This is a standard for executable files and shared object files, such as libraries. We'll take a look at the ELF header format shortly. What might catch your eye is that the two executables WD and hello are identified as Linux standard base LSB shared objects, and the object file WD-O is identified as an LSB relocatable. The word executable is obvious in its absence. Object files are relocatable, meaning the code inside them can be loaded into memory at any location. The executables are listed as shared objects because they've been created by the linker from the object files in such a way that they inherit this capability. This allows the address space layout randomization (ASMR) system to load the executables into memory at addresses of its choosing. Standard executables have a loading address coded into their headers, which dictate where they're loaded into memory. ASMR is a security technique. Loading executables into memory at predictable addresses makes them susceptible to attack. This is because their entry points, and the locations of their functions, will always be known to attackers. Position-independent executables (PI) positioned at a random address overcome this susceptibility. If we compile our program with the GCC compiler and provide the no PI option, we'll generate a conventional executable. The O output file option lets us provide a name for our executable. GCC hello no PI hello C. We'll use file on the new executable and see what has changed. File hello. The size of the executable is the same as before, 17 KB. LSHL hello. The binary is now identified as a standard executable. We're doing this for demonstration purposes only. If you compile applications this way, you'll lose all advantages of the ASMR. Why is an executable so big? Our example hello program is 17 KB, so it could hardly be called big. But then, everything's relative. The source code is 120 bytes. Cat hello, C. What's bulking out the binary if all it does is print one string to the terminal window? We know there's an ELF header, but that's only 64 bytes long for a 64-bit binary. Plainly, it must be something else. LSHL hello. Let's scan the binary with the strings command as a simple first step to discover what's inside it. We'll pipe it into less strings hello, less. There are many strings inside the binary. Besides the hello, geek world, from our source code, most of them are labels for regions within the binary, and the names and linking information of shared objects. These include the libraries, and functions within those libraries, on which the binary depends. The LDD command shows us the shared object dependencies of a binary. LDD hello. There are 3 entries in the output, and 2 of them include a directory path, the first does not. Linux-vdso.so, Virtual Dynamic Shared Object (VDSO), is a kernel mechanism that allows a set of kernel space routines to be accessed by a user space binary. This avoids the overhead of a context switch from user kernel mode. VDSO shared objects adhere to the executable and linkable format, ELF format, allowing them to be dynamically linked to the binary at runtime. The VDSO is dynamically allocated and takes advantage of ASMR. The VDSO capability is provided by the standard GNU-C library if the kernel supports the ASMR scheme. libc.so.6, the GNU-C library shared object. lib64, ld Linux x86 64.so.2, this is the dynamic linker the binary wants to use. The dynamic linker interrogates the binary to discover what dependencies it has. It launches those shared objects into memory. It prepares the binary to run and be able to find and access the dependencies in memory. Then, it launches the program. The ELF header. We can examine and decode the ELF header using the readelf utility and the h-file header option. Readelf h hello. The header is interpreted for us. The first byte of all ELF binaries is set to hexadecimal value hexadecimal 7f. The next 3 bytes are set to hexadecimal 45, hexadecimal 4c, and hexadecimal 46. The first byte is a flag that identifies the file as an ELF binary. To make this crystal clear, the next 3 bytes spell out ELF in ASCII. Class indicates whether the binary is a 32 or 64-bit executable. 1 equals 32. 2 equals 64. Data indicates the endianness in use. Endian encoding defines the way in which multibyte numbers are stored. In big endian encoding, a number is stored with its most significant bits first. In little endian encoding, the number is stored with its least significant bits first. Version, the version of ELF currently. It's 1. OS, ABI, represents the type of application binary interface in use. This defines the interface between 2 binary modules, such as a program and a shared library. ABI version, the version of the ABI. Type, the type of ELF binary. The common values are et_rel for a relocatable resource, such as an object file, et_exec for an executable compiled with the no-py flag, and et_dyn for an ASMR-aware executable. Machine, the instruction set architecture. This indicates the target platform for which the binary was created. Version, always set to 1. For this version of ELF. Entry point address, the memory address within the binary at which execution commences. The other entries are sizes and numbers of regions and sections within the binary so their locations can be calculated. A quick peek at the first 8 bytes of the binary with hexdump will show the signature byte and ELF string in the first 4 bytes of the file. The C canonical option gives us the ASCII representation of the bytes alongside their hexadecimal values. And the N number option lets us specify how many bytes we want to see. Hexdump CN8 hello. Objdump in the granular view. If you want to see the nitty-gritty detail, you can use the objdump command with the D disassemble option. Objdump D hello less. This disassembles the executable machine code and displays it in hexadecimal bytes alongside the assembly language equivalent. The address location of the first by in each line is shown on the far left. This is only useful if you can read assembly language, or you're curious what goes on behind the curtain. There's a lot of output, so we piped it into less. Compiling and linking. There are many ways to compile a binary. For example, the developer chooses whether to include debugging information. The way the binary is linked also plays a role in its contents and size. If the binary references share objects as external dependencies, it will be smaller than one to which the dependencies statically link. Most developers already know the commands we've covered here. For others, though, they offer some easy ways to rummage around and see what lies inside the binary black box.